Welcome to the Deep Dive. We're here to break down complex topics, give you the key insights, and maybe uncover a few surprises along the way. Today, we're tackling something that sounds straight out of sci-fi, but it's very real. The unbreakable link. Quantum cryptography and communication.
It's a fascinating area, definitely.
What really grabs me is this duality in quantum mechanics. The same weird quantum rules that could let future computers break today's codes.
Like Shor's algorithm threatening RSA.
Exactly. Those same rules can apparently create communication that's, well, fundamentally unbreakable.
That's the promise, yeah.
Sure.
Security based on physics, not just hard math problems.
So our mission today is to unpack that. We'll use a Q&A format, drawing on some great source material to explore how it all works.
Sounds good.
We'll cover a few key things. First, the big difference between classical and quantum security principles.
Right.
Then we'll dive into quantum key distribution, QKD, what it is, why it's so secure.
That information theoretic security idea.
Yep. And we'll get into the nitty-gritty of the famous BB84 protocol.
It's the classic example, yeah.
After that, maybe the weirdest part. Quantum teleportation. What does that really mean for communication?
Not quite Star Trek, but still pretty amazing.
Definitely.
Yeah.
Then we'll look ahead. The vision for a quantum internet. Its applications. Like secure cloud computing, better sensors.
Huge potential there.
And finally, we'll ground ourselves a bit. What are the practical challenges? Is the security really absolute in the real world?
An important distinction, that theoretical versus practical security.
Okay, let's unpack this then. We've established quantum computers could be massive code breakers. So how can those same quantum principles flip the script and create truly secure communication? What's the fundamental difference in how classical and quantum cryptography think about security?
Yeah, it's that duality again.
Quantum cryptography basically weaponizes the weirdness of quantum mechanics for security. Things like the observer effect, just looking at a quantum state changes it, and the no cloning theorem, you can't perfectly copy an unknown quantum state. These become features, not bugs. So think about classical encryption, like RSA. It works because factoring large numbers is, well, really hard for current computers. We call that computational hardness.
Right, it's based on a mathematical problem being too tough.
Exactly. But it's an assumption. It's security that's probabilistic, maybe temporary.
Yeah.
If someone finds a faster algorithm or builds a powerful enough quantum computer running Shor's,
Poof, the security evaporates.
pretty much. Now, quantum cryptography, especially QKD, offers information theoretic security. It's not based on math being hard, it's based on the laws of physics.
Laws of physics, how does that work?
Well, because of things like the observer effect. Any attempt by an eavesdropper, let's call her Eve, to intercept and measure the quantum information being used to create the key, that act of measurement will disturb the system.
So she leaves fingerprints.
It's exactly detectable fingerprints. Alice and Bob, the legitimate users, can check for these disturbances. If they find errors above a certain level, they know someone was listening. Eve simply cannot gain information without revealing her presence, even if she has infinite computing power. It's a total shift from it's too hard to break to it's physically impossible to break without being caught.
Wow. That's a huge difference. Not just harder, but fundamentally different rules. Okay, so let's zoom in on this quantum key distribution, QKD. What's its main goal, and how is it different from just encrypting a message?
Good question. QKD's primary job is not to encrypt the actual message you want to send.
Oh, okay.
Its sole purpose is for two parties, Alice and Bob, to generate and share a secret random key. Once they have this secret key and they've verified it's secure, then they use it with traditional classical encryption methods like AES to encrypt their actual data.
So QKD is like a super secure courier delivering the secret key.
That's a great analogy. It ensures the key itself hasn't been compromised during creation. The guarantee is, if Eve tries to listen in on the key generation, Alice and Bob will know about it. It secures the foundation before you build the house.
Got it. So it secures the key, then you use that key classically. And the sources mention the BB84 protocol a lot. You said it uses the observer effect and no cloning. Can you elaborate on how those two principles make BB84 work?
Sure. BB84 from Bennett and Broussard back in '84 was really groundbreaking. It uses single photons. The observer effect is key. Measuring a quantum system, like checking the polarization of a photon, forces it out of any superposition it was in and disturbs it. You can't just peek without changing things.
Okay, measuring changes it. What about no cloning?
The no cloning theorem is equally crucial. It says you cannot make a perfect identical copy of an unknown quantum state. You can't just intercept Alice's photon, copy perfectly, send the copy to Bob, and keep the original to measure later. It's physically impossible, so put them together. Eve can't copy the photon. If she tries to measure it to learn the key bit, she inevitably disturbs it because of the observer effect. When she tries to send a new photon to Bob to cover her tracks, it won't be identical to the original, and her measurement might introduce errors. These errors are the telltale sign she was there.
It sounds like a really delicate process, like walking on quantum eggshells. Can you walk us through the first bit? How do Alice and Bob actually start making this key with DB84? What choices do they make?
Absolutely. It starts with Alice. She wants to generate a random string of bits that will become the key. For each bit, she does two things randomly. First, the bit value. Is it a 0 or a 1?
No.
Second, the encoding basis. She randomly chooses how to represent that 0 or 1 using photon polarization. She might use the rectilinear basis, say horizontal polarization for 0 and vertical for 1. Or she might use the diagonal basis, say 45 degrees for 0 and 135 degrees for 1.
Okay, so two random choices per bit. Value and basis.
Exactly. She sends a stream of photons encoded this way to Bob. Critically, she keeps her sequence of basis choices secret for now.
And what does Bob do when these photons arrive?
Bob also makes a random choice for each photon he receives. He randomly chooses which basis to use for his measurement, rectilinear or diagonal. He has absolutely no idea which basis Alice used for any given photon.
So he's just guessing the basis each time.
He's guessing the basis, yeah. And that guessing is fundamental to the security.
Okay, this is where it gets interesting. What's the difference if Bob guesses the right basis versus guessing the wrong one?
This is the core mechanism. If Bob happens to randomly choose the same basis that Alice used to encode the photon, he's guaranteed to measure the correct bit value she sent.
Guaranteed.
Guaranteed. If Alice sent a 1 using the vertical polarization in the rectilinear basis, and Bob measures using the rectilinear basis, he will measure vertical, a perfect transmission.
Okay, and if he guesses wrong?
If Bob chooses the wrong basis, say, Alice used rectilinear, but Bob measures in diagonal, then the outcome of his measurement is completely random. He has a 50% chance of getting a 0 and a 50% chance of getting a 1, completely uncorrelated with the bit Alice actually sent.
So mismatching bases scrambles the result for Bob.
Exactly. From his perspective, if he used the wrong tool, the information he gets is just noise.
Fascinating. Okay, so Alice sends, Bob measures, lots of random choices involved. What happens after all the photons have been sent and measured? You mentioned a public discussion or sifting.
Right. After the quantum part is done, Alice and Bob communicate over a normal classical channel. This could be a phone line, the internet, importantly. It can be public. Eve can listen to this part.
Okay, so what do they talk about?
Bob tells Alice, publicly, only the sequence of bases he used for his measurements. He absolutely does not reveal the results, the zeros and ones he measured.
Just the bases.
Just the sequence of bases. Alice compares this public list to her private list of the bases she used for sending. They then publicly agree to discard all the bits where their basis choices didn't match.
Because those results are random anyway if the bases were wrong.
Precisely. They keep only the bits where they happen to use the same basis. On average, this will be about half the bits they started with. This remaining set of bits is called the sifted key.
So now they have a shorter key, but one where ideally they should have the same values because they use the same bases.
In a perfect world, yes. If there was no noise and no eavesdropper, their sifted keys should be identical.
And this is where they check for Eve, right? How do they use the sifted key to see if someone was listening?
Exactly. Now comes the crucial eavesdropping detection step. Alice and Bob agree to sacrifice a randomly chosen subset of their sifted key bits.
Sacrifice, meaning they reveal them.
Yes. They publicly compare the actual bit values, the zeros and ones, for this chosen subset over that same classical channel.
Okay. How does that reveal Eve?
Remember Eve's problem?
Yeah.
To learn the key, she had to intercept and measure the photons. Like Bob, she didn't know Alice's basis choices. So inevitably, Eve would have measured some photons using the wrong basis.
Right, just like Bob might have.
But when Eve measures incorrectly, she disturbs the photon's state. Then she has to send a new photon on to Bob to try and cover her tracks. But because of the disturbance, the photon Bob receives might be wrong, even if Bob uses the same basis as Alice.
So Eve's incorrect measurements introduce errors into the bits where Alice and Bob should have matched.
Precisely. So when Alice and Bob compare their subset of sifted key bits, if Eve was listening, they'll find mismatches. They'll see errors that shouldn't be there. They calculate the quantum bit error rate, or QBER. if this QBER is higher than what they'd expect from natural noise in the system.
They know someone messed with the photons.
They know the key is compromised. They discard the entire key and start over. If the error rate is low enough, they can be confident E wasn't there. Then they perform two final classical steps: error correction to remove the few errors caused by natural noise, and privacy amplification to distill the key down, making it even more secure against any partial information Eve might have somehow gained. The result is a shared secret key whose security is guaranteed by physics.
That's incredibly clever. The check itself relies on the unavoidable errors an eavesdropper introduces. Okay, let's shift gears to something equally, if not more, mind-bending. Quantum teleportation. What's actually being teleported? Because, like you said, it's not people or objects, right?
Definitely not people. That's pure sci-fi. Quantum teleportation is very real, experimentally proven, but it's about transferring information, specifically the quantum state of a particle.
The state, like its properties.
Exactly. Imagine a qubit has a specific state. Maybe it's in a particular superposition. Teleportation is a protocol to transfer that exact state onto another qubit at a distant location, without the state physically traveling through the space between them. The original state is destroyed in the process, and an identical copy appears on the target qubit.
Okay, destroying the original and recreating it elsewhere. Sounds delicate. What do you need to make it work? What are the ingredients?
You need two key things to teleport the state of qubit C from Alice to Bob. First, Alice and Bob need to share an entangled pair of qubits beforehand. Let's say Alice holds qubit A and Bob holds qubit B, and A and B are entangled.
Entangled, meaning linked in that spooky quantum way.
That's the one. Linked instantly, no matter the distance. The second ingredient is a classical communication channel. Just like in QKD, they need a regular way to send classical information, like bits over a phone line.
Entanglement and a phone line, okay. How does the protocol actually play out? How does Alice's action change Bob's qubit?
It's a neat three-step process. First, Alice performs a special kind of joint measurement, called a Bell state measurement, on her two qubits, the one she wants to teleport, C, and her half of the entangled pair, A.
Measuring them together.
Yes. This measurement does two things. It tells Alice one of four possible outcomes: classical information, like 0, 1, 10, or 11, and crucially, it destroys the original state of qubit C. The information is now encoded in the relationship revealed by the measurement.
Okay, original state gone, Alice has classical bits.
Step 2. Alice uses that classical channel, the phone line, to send those two classical bits of measurement outcome to Bob.
And then this takes time, limited by the speed of light.
Exactly. No faster than light communication here. Step 3. Bob receives the two classical bits from Alice. Depending on which of the four possible results he receives, he performs one of four specific correction operations, like applying a particular quantum gate, on his qubit B, his half of the original entangled pair.
He adjusts his qubit based on Alice's message.
Right. And the moment he applies the correct operation corresponding to Alice's measurement result, his qubit B instantly transforms into an exact replica of the original quantum state that qubit C had before Alice measured it. The state has been teleported.
Wow. So the entanglement provides the link, and the classical message tells Bob how to tune his qubit to match the original. It's amazing that classical info is still so vital.
It really is. You need both quantum entanglement and classical communication working together.
Both QKD and teleportation seem like foundational technologies for something bigger. People talk about a future quantum internet. What's the vision there? And what's maybe the biggest hurdle to building it?
The quantum internet vision is essentially a network connecting quantum devices, processors, sensors using quantum communication channels. It wouldn't replace our classical internet, but would work alongside it, enabling new functions. Think distributing entanglement globally.
Okay, connecting quantum devices sounds complex. What's the main roadblock?
The single biggest challenge is definitely building effective quantum repeaters.
Repeaters? Why are they needed?
Because quantum states, especially encoded in photons traveling through optical fibers, are incredibly fragile. They get absorbed or lost over relatively short distances, much shorter than classical signals can travel. And you cannot just use a classical amplifier like we do for internet signals today.
Right, because that would measure and destroy the quantum state.
Exactly. So a quantum repeater is a much more sophisticated device. It uses concepts like entanglement swapping and purification, essentially, creating entanglement across smaller segments and linking them together without directly measuring the information qubit itself. Developing these repeaters so they're efficient, reliable, and work over long distances is the critical bottleneck for realizing a large-scale quantum internet. It's a major engineering challenge.
A huge challenge. But if we can overcome it, if we get these quantum repeaters working and build this quantum internet, what kind of game-changing applications could we see?
Oh, the possibilities are really exciting. First, obviously, fundamentally secure communication on a global scale using QKD networks. Unhackable, essentially.
That alone is huge.
Definitely. Then, secure quantum computing in the cloud. Imagine accessing a giant quantum computer remotely, knowing your input data, the computation itself, and the output are all perfectly secure, thanks to quantum protocols.
So privacy even when using someone else's quantum computer.
Precisely. Also, enhanced sensing. You could create networks of entangled sensors, think atomic clocks, telescopes, maybe even medical sensors that achieve sensitivities and resolutions far beyond what's possible classically. Better GPS, maybe new ways to see into the body or out into the universe.
Wow.
And finally, distributed quantum computing, linking multiple smaller, perhaps less powerful quantum computers together through the quantum internet to effectively act as one larger, more capable machine. This could accelerate our progress towards solving really complex problems.
Secure communication, secure cloud computing, better sensing, linked quantum computers. It really sounds transformative. Okay, let's try and tie this together. Could you just summarize one more time? What is the absolute core difference between the security guarantee of something like classical RSA versus quantum QKD?
Absolutely. It boils down to the foundation. Classical encryption, like RSA, relies on computational hardness. It assumes certain math problems are too hard for current computers. As probabilistic security, we're pretty sure it's safe, but we can't prove it won't be broken tomorrow by a new algorithm or computer. It's security based on an assumption.
Okay, assumption-based.
Quantum key distribution, QKD on the other hand, provides information theoretic security. Its security is based on the fundamental laws of physics. The observer effect, no cloning, these aren't assumptions, they're how the universe works. An eavesdropper is physically constrained. It's absolute and permanent security against eavesdropping on the key generation, regardless of future computing power. It's security based on physical impossibility.
Physical impossibility. That's such a powerful concept. But is it truly absolute in the real world? Are there practical caveats? We touched on side channels earlier.
That's a crucial point. The theory of QKD, the underlying physics, provides that absolute security guarantee against eavesdropping on the quantum channel itself. However, practical implementations, the actual hardware boxes you build, are not perfect.
Right, the engineering side.
Exactly. Real-world devices can have flaws or leak information in ways not covered by the core theory. These are often called side-channel attacks. Maybe the device emits slightly different amounts of heat, or it takes slightly different amounts of time depending on the secret key bits, or maybe the detectors aren't perfect. If Eve can exploit these implementation weaknesses, she might gain information without needing to directly attack the quantum channel in the way the theory forbids.
So the physics is sound, but the engineering needs to be incredibly careful to avoid creating new non-quantum vulnerabilities.
Precisely. There's a big difference between theoretical security proofs and the security of a deployed real-world system. Achieving practical security requires very careful engineering, testing, and often certification processes to ensure these side channels are closed off.
What an incredible journey. We started with this strange quantum duality, breaking codes and making unbreakable ones. We saw how QKD uses physics itself, like the observer effect, as an alarm system. Then quantum teleportation, moving information without moving the carrier. And finally, this vision of a quantum internet built on things like quantum repeaters, promising truly secure communication, cloud computing, sensing. It really feels like we're shifting from security based on this math is hard to this is physically impossible to break undetected.
It's a fundamental shift in perspective, absolutely. Yeah. And it leads to some deep questions, doesn't it?
Like what?
Well, as we get closer to this reality, maybe even a world with a widespread quantum internet offering perfect communication secrecy. How does that change things? How will our ideas about privacy, about surveillance, about even global power balances need to adapt when truly unbreakable, physics-guaranteed secure communication becomes a widespread reality?
That's a huge question to think about. What does a world with perfectly private communication look like? A profound thought indeed. Thank you for joining us on this fascinating deep dive into quantum cryptography and communication. If you enjoyed exploring this with us, please subscribe to Tech AI and Beyond wherever you listen. We'll keep bringing you insights into the tech shaping our future. Until next time, keep exploring.